Moments of inertia, type 2, angular velocity. So in 1996 we had a uniform circular disk, or, and can move freely about a smooth pivot at a point A and on its circumference. When its plane is vertical and the diameter AB is horizontal, the point B is given a velocity P vertically downwards. Okay, so it's not starting from rest. So the first thing we want to do is find the angular velocity of the disk when B is vertically below A, in other words, at the position B1. So before we can find angular velocity, first thing we need to know is what's our moment of inertia. So if we're looking at the moment of inertia, the first thing we should note is that the pivot point is A, right? So our fulcrum is at the point A, and yet when we're finding moments of inertia of our disk, it's normally through its centre of gravity, which is the point C. And therefore, if we're looking at the point C and we were to place our pen at C and our pen at A, we will notice that these are parallel to each other, and therefore we're going to have to use the parallel axis theorem. So in other words, if we're getting the moment of inertia of the disk through the point A, we're going to have to get the moment of inertia through the point C for the disk plus md squared. So in other words, we're using our parallel axis theorem. And this is, of course, in our maths tables, which is page 53. And we're doing that because A is parallel to C. Okay, so what's our moment of inertia for the disk through its centre? Well, through the disk, through its centre, it's a half mr squared. And the mass is m and the radius is r, so that's actually just going to stay as a half mr squared. So always be careful, you don't assume that the mass is m, sometimes it could be 2m or 3m, and the radius isn't always going to be r either, okay? So just make sure you're checking the mass and checking the radius before using your moments of inertia equations. So of course m is the mass of the disk, and then d is the distance between these 2 points A and C, which is of course our radius, or if I mark that on the diagram, so that's going to be our distance between the two axis points, so that's going to be mr squared. So our moment of inertia through the axis point A is going to be 3 over 2 mr squared. So we were getting 5 marks for working out our moment of inertia. Okay, so now we have our moment of inertia, we have to figure out how we're going to get our angular velocity. And of course, for our angular velocity, we need to be looking at our energy. So in other words, our energy before should be equal to our change in energy after. So we have to look at what is our starting position and what is our ending position. So we're trying to find the angular velocity of the disk when B is vertically below A, given that it's starting with its plane vertical and the diameter is horizontal. The point B is given a velocity P vertically downwards. So in other words, if we're drawing our starting and our end position, as best I can, then we have something like this. So that's our, and exaggerating our position point A there. So if I mark through here, we have C, and again here we have C. Then of course, if I'm marking in my radius on this diagram, that's my radius and that's my radius, and of course this distance here is r and this distance here is also r. Okay, so we have to pick what our standard position is going to be. So I always take my standard position through the lowest centre of gravity of the system. So I'm going to mark the centre of gravity of the disk in its second position as my standard position. So we'll always work out h in relation to this. Okay, given that it is rotating in this direction here. In other words, it has angular velocity. Okay, so if we're looking at our energy, we'll say that before must equal after. So in other words, our change in velocity before, change in energy, I should say, before and after will be equal. So beforehand, our energy, well, it's starting with a position above the ground, so therefore it's going to have potential energy. And then we also have to look at the fact that it's given a velocity downward, and therefore it's also going to have angular velocity to begin with. So therefore we say beforehand, the energy is going to be its potential energy and its kinetic energy, where its potential energy will be its mass times gravity times height. Well, the height above the standard position, we can see here is r. So let me mark that in. So this is h. So it's the centre of gravity above the standard position beforehand is h. So that's just going to be mgh for the potential energy. And then we have a half times I. Well, we said our moment of inertia, if we go back, is 3 over 2 mr squared. Times the angular velocity squared. Well, angular velocity, how are we going to get that? Well, we know that it is given a initial velocity, if we go back, of p. Okay, so it's given a velocity p vertically downwards. So therefore, if I'm looking for the angular velocity, omega is going to equal p over r, where r is the radius of rotation. Now again, just be careful not to just stick in or, because if you look at this, the radius of rotation is actually going to be 2r. Okay, so if that is rotating all the way around, what we'll end up with is a whole, so our angular velocity given down. So therefore this is 2r for the radius as the circles continue to rotate around. So therefore the radius of the path is 2r. So putting that in, that's p over 2r, and I have to square that. So therefore our energy beforehand is going to be mgh, and if I square out and multiply out my brackets here, I'm going to end up with 3 over 4 mr squared times p squared over 4r squared. And of course we can see our r squareds are going to cancel there, and that leaves me with mgh, sorry, h. I've just noticed there that h obviously is the radius. If I go back there, look, h is the value or there. So that should be mg or, okay. And then if I multiply my brackets here, that leaves me with 3mp squared over 16. Okay, so this is equation 1 for the energy beforehand, and we were getting 5 marks for that. And then I have to do the same for after. So what's the energy after going to be? So again, afterwards, our potential energy and our change in kinetic energy. So at the end, when it gets to position, the second position, so down here at B1, then what we can see is the standard position is actually passing through the centre of gravity, and therefore the height of the centre of gravity above the standard position is actually going to be 0. So that's why it's always nice to choose your centre of gravity of the lowest part of the system to be your standard position. It simplifies your calculations. And again, if we look at the kinetic energy, well, our moment of inertia is 3 over 2 mr squared. And we want to know what is the angular velocity at this point. So we're actually looking for omega. So if I simplify that, that gives me 3 over 4 mr squared omega squared. So now I have a second equation here for our energy. And again, we were getting 5 marks for this. So obviously, our energy before should equal our energy after because of our conservation of energy. So if we equate 1 and 2, we can then simplify and get omega on its own. So we have mg or, and 3 over 16 mp squared is equal to 3 over 4 m r squared omega squared. And I can, of course, divide across there by m. And if I simplify that, well, what do I end up with? Well, if we multiply everything across there by 16, well, then I get 16 times GR plus 3p squared is equal to 4 goes into 16 4 times, so that's 12 r squared omega squared. And if I divide everything across by 12 r squared, well, that gives me 16 GR plus 3p squared over 12 r squared. And then I just need to get the square root of both sides. So 16 GR plus 3p squared all over 12 r squared. And I can't simplify that down any further, so therefore that is my angular velocity. So rad per second if we were looking to use a unit. Okay, so the second part of the question then says, find the value of P. And we have to find the value of P in terms of r, and it's if B just reaches the point where it is vertically above A. So in other words, we're going to be at position B2. So in other words, if I'm looking at this part of the question, my starting position was the original starting position, and it's now going to end up here. So it's going to have gone all the way around and back up to that position. So again, there's C, there's A, and again, there's C. And again, our radius Maybe we just redo that diagram, sorry. So I'll start with the top one. It's a bit better. Sorry, my circles aren't great. So that's A, and there's C, and there's C. And of course then this is the radius. Okay, so again, this time I'm going to take my standard position again as the centre of gravity of the lowest part of the system. So in other words, through C. And of course then afterwards, my height above the standard position is going to be r. And this is my angular velocity. It's rotating in that direction. So same as before, we're going to start with our energy before should equal our energy after, where before is our mgh plus a half I omega squared. And therefore beforehand, our mass times g, well, h, our standard position, is the centre of gravity, and therefore at the start it has no potential energy with relation to its standard position, plus a half I, we said was 3 over 2 mr squared times omega squared. Well, omega is still our p over 2r as in the previous question, because v was equal to omega r and v was p, and our radius of rotation was 2r. So if I simplify that, I end up with 3 over 16 mp squared as my equation 1 this time. And then after, our potential and our kinetic energy. Well, our height above the standard position is r, our radius. We can see that in our diagram. We have our 3 over 2 mr squared for our moment of inertia, and we are told, let's go back to the question, that it just reaches the point. Okay, so if it just reaches that point, that means it just has enough has just enough momentum to get to the point B2, which means that it is just coming to an end. So in other words, its angular velocity is going to be 0 at this position. Okay. And therefore that all cancels, leaving us with just mg or for our second equation. Okay, so we were getting another set of 5 marks for our 2 equations this time. So again, we want to equate 1 and 2. And when we equate 1 and 2, we have 3 over 16 mp squared is equal to mg or. So our masses are going to divide there. And if I want to get p squared on its own, I multiply across there, I get 16g or over 3. And then get the square root of both sides, and that gives me the square root of 16g or all over 3. So that is our value for p. Okay, so we had 5, 10, 15, 20, 25, 30 mark question. So a nice angular velocity question there. So it's always about drawing a good diagram so you can get your standard position marked out, and be careful of your radius of rotation then too.